So the final skill we want to develop is the retrosynthesis of enolates. And by now you've seen that enolates react with a variety of different functional groups as electrophiles. So the possible electrophiles that we've come across are things like aldehydes and ketones, esters, anhydrides, or acid chlorides, alkyl halides, and finally the alpha-beta unsaturated carbonyls. The most difficult part of this section of the course is actually designing a synthesis. The strategy you should take is retrosynthesis, where you're thinking about things backwards. Where you take a molecule and you break it apart into smaller portions by making sort of these key bond disconnections. But in this section of the course, we have to recognize that the particular functional groups can be made by a specific reaction with enolates. So the nucleophile is, of course, always an enolate. So when you're making carbon-carbon bonds, one of those carbons will be capable of forming an enolate. And you should simply circle this portion of the molecule so that you know it's what forms the enolate. The other carbon of that new carbon-carbon bond will be one of the four choices that we have here. And so by looking at a particular carbon-carbon bond, you should be able to identify which electrophile you need. And all that is left to do is to break the carbon-carbon bond into these components and draw an arrow with a set of reagents. So let's try to do an example. Let's say we have this molecule here. We want to make this molecule. If we try to find an easy way to make this molecule, we should first try to identify where the enolate-like carbon is, right? And it should be alpha to a carbonyl. And there's really only one choice, right? Because there's only one carbonyl, right? So this means that this half right here is going to be our enolate half. And so we're making this carbon-carbon bond right there. That means that the other half is going to be our electrophile half. So we got to stitch these two halves together via this carbon-carbon bond I show in green by some reaction. So we know that the enolate is going to be nucleophilic, and so the enolate will look like this. And of course we can have a resonance form where we draw the negative charge on oxygen. Okay. And this enolate can form by deprotonation of an ester with an appropriate base. And so we can draw a retrosynthetic arrow indicating that it comes from that methyl ester. And we can treat it with a base, let's say sodium methoxide. Right, so we take this and we add sodium methoxide and we generate that enolate. The only question we have left is what's the other piece? What's the electrophile? And we know that our end product is an alcohol. And so we have choices. We have the aldehyde or ketone, the ester anhydride or acid chloride, alkyl halide, or the alpha-beta unsaturated carbonyl. And only one of these will actually work, and it turns out that it's the aldehyde. Right? And how do we know that? Well, we know that it needs to come from a piece that has this kind of reactivity. All right? And so this kind of reactivity suggests that you have an aldehyde, which has, of course, a delta positive charge on the carbonyl carbon. Right, so if we were to take these two halves and bring them together to form this new carbon-carbon bond, that would be an Aldol reaction. Right, so the reaction scheme that we would draw is the following. we would take methyl acetate, react it with sodium methoxide, and then benzaldehyde to give us the beta-hydroxy ester in this case, where we form this new carbon-carbon bond right here. Okay, so let's see if we can identify the enolate and electrophile pieces in a couple of other types of functional groups. All right, so let's start with this one. All right, so if we want to make this molecule, we have to identify an enolate piece and an electrophile piece. And to be consistent, I'm going to circle the enolate piece with a blue line and the electrophile piece with a red line. So we could basically identify this piece right here as being our enolate piece, and this piece here as being our electrophile piece. All right, so the enolate piece would, of course, come from this enolate. The electrophile piece would have this kind of reactivity, where we've got a doubly bonded oxygen with a positive charge on the carbonyl carbon. So where would those two things come from? They would need to come from, in this case, ethyl acetate plus deprotonation with sodium ethoxide. And in the case of the electrophile, it would need to come from a piece that has some sort of leaving group on it. Let's say another molecule of ethyl acetate. Now, why do we choose this? Because it was one of those four choices. It's not an aldehyde or ketone, but rather it's an ester anhydride or acid chloride. Obviously, you can't make that bond with an alkyl halide nor with an alpha beta unsaturated carbonyl. And so this reaction that we're talking about here would be a Claisen condensation. Okay, and it comes from the fact that you have a 1,3 dicarbonyl, and you might recall that we talked about forming 1,3 dicarbonyls as coming from Claisen condensations. Just like we said that beta-hydroxycarbonyls come from aldol reactions. Now that's not the only way that you can disconnect that molecule. So let's draw another type of reaction, but this time let's disconnect with a different enolate piece. Let's say that's the enolate and that's the electrophile. Okay, so for that we need an enolate piece that looks like this and an electrophile piece that looks like this. So the enolate piece will come from acetone and reaction or deprotonation with sodium ethoxide. And in the case of the electrophile, it needs to be one of those choices, aldehyde or ketone, ester anhydride or acid chloride, alkyl halide, or alpha beta unsaturated carbonyl. And the only one that fits is to put a leaving group on it to make it look like an ester. And so again, this is another example of a Claisen condensation where you're starting from a different nucleophile and a different electrophile. So again, this is still a 1,3 dicarbonyl, but now we've disconnected it in a different way. All right, let's try another example. Let's try this one. Okay, so in this particular example, we need to search for an enolate piece and an electrophile piece. So I'm going to say the enolate piece is this one, and the electrophile piece is this one. Okay, so the enolate piece would, of course, look like this. It's going to be negatively charged. The electrophile piece will have reactivity that resembles that. And so we can form the enolate by simple deprotonation of acetone. Let's use sodium methoxide again. But the reactivity of that electrophile piece, it needs to be either aldehyde or ketone, ester anhydride or acid chloride, alkyl halide, or alpha beta unsaturated carbonyl. And so in order to have some sort of just regular old carbon that has a positive charge on it, you can just attach a leaving group onto it, and you can generate an alkyl halide. And so this reaction is just enolate alkylation. So alkyl halide is our electrophile. One more way we can disconnect this molecule. We could say that this is the enolate piece, and this is the electrophile piece. And so if that's the enolate, we can, of course, comes from deprotonated cyclohexanone. The electrophile piece is this one. And so we know that the enolate comes from a deprotonation of cyclohexanone. So let's just say cyclohexanone and sodium methoxide. And in the case of the electrophile, we know that that positive charge exists beta to the carbonyl. And so in order to get reactivity at the beta position to a carbonyl, we can think of this as being coming from an alpha beta unsaturated carbonyl. And so this particular carbon has delta positive on it, right? It's got the biggest lobe in the molecular orbital description. And so this reaction, when we bring these together, is called a Michael addition. It's the last electrophile that we could potentially react enolates with. So we've now really developed a strategy for identifying important functional groups like the beta hydroxycarbonyl, the 1,3-dicarbonyl. In the last two cases, we actually have a 1,5-dicarbonyl. So if you see a 1,3-dicarbonyl, you're going to think, okay, I need to do a Claisen condensation. If you think a 1,5-dicarbonyl, you can think, I need to do a Michael addition. Or if there's a beta hydroxycarbonyl, you need to do an Aldol reaction. And so there's one pesky functional group which gives us trouble, and that's the alpha beta unsaturated carbonyl. How do we form that? And this is really a process that involves the E1CB and the Aldol. And so let's say we have this molecule here. So this is an alpha beta unsaturated carbonyl. This can come from an E1CB from a beta hydroxycarbonyl. Okay, so you can basically undergo E1CB here to generate that alpha beta unsaturated carbonyl. But this beta hydroxycarbonyl can also come from an aldol reaction. And so the aldol reaction that we would have would be something that looks like this, where we have those two carbonyls coming together and performing an intramolecular aldol reaction. And we can actually disconnect this even further by doing a Michael reaction, Michael addition. And the Michael addition will come from an aldehyde and an alpha beta unsaturated carbonyl plus some base. let's say LDA. So how do we know that this is the case here? How can we think of this retrosynthetically? Well, we can think of disconnecting this alpha-beta unsaturated carbonyl and the ultimate product here by forming that double bond via an E1CB mechanism. And then if we try to identify in the beta-hydroxycarbonyl an enolate piece and an electrophile piece, we see that this is going to be our enolate piece and this is going to be our electrophile piece. And so that gives us a ketone in the blue and an aldehyde in the red. And it's just that those two things are connected to one another because they're it's an intramolecular reaction that we only get a single molecule. And then, of course, we can disconnect the 1,5-dicarbonyl into an enolate piece and an electrophile piece like this, and that's just a Michael addition. Okay, so this is the alpha-beta unsaturated carbonyl. And this comes from E1CB from a beta-hydroxycarbonyl. And we know that a beta-hydroxycarbonyl can be disconnected through an aldol reaction to a 1,5-dicarbonyl. And that 1,5-dicarbonyl can be disconnected through a Michael addition from a carbonyl and a alpha-beta unsaturated system. And so this series of steps where you have E1CB, aldol, and Michael, in the forward direction, this would be a Robinson annulation. So without even realizing it, you've just completed the Robinson annulation. The key is to start by identifying the functional groups that are easy to form and break the bonds until you arrive at something new that suggests another key bond disconnection. So all of these individual steps we've actually done on the previous slide, but taken together, they form a sequence known as the Robinson annulation.